Alright, Matt here, again with Peervids, and today we are doing nuclear chemistry. This is chapter 3 in your Barron's book. Now, it's going to be probably a long video, just because there's a lot of material. I don't think it's too hard, mostly just basic addition and subtraction. But then Halflife and radioactive decay is a little harder. But I drew some symbols for you. These are ones you're going to need to know for nuclear chemistry, because you'll get things like, oh, this is decaying and loses a beta particle, or loses a proton. What does it turn into? So it's just important to learn these. So you'll learn them with practice. Don't think you need to just memorize the table before you start, but they're important. Alright, so here's the first example reaction that the Barron's book gives you. It's very simple, and to explain how it works. So first they give you radon, if you don't remember from earlier, this number right here, the 222, that is the atomic molar mass, and the number down here, 86, is its number on the chart, or how many protons it has. So this reaction says that it decays or whatever, and it decays and loses a alpha particle. So since it loses the alpha particle, you're gonna, on the other side, you're gonna have the alpha particle over here. It can also be written as alpha symbol 2, 4. They just use helium because it is pretty much a helium atom, because it has 2 protons and 2 neutrons, so either works. But then, so how you get to the polonium is you just go across. You know there has to be helium over here, and 4 plus what number there? 4 plus a number will make 222, because it's losing 4 from its mass. So 218 will be the new mass, and then you see down here that it also has 2 protons. So 2 plus an x number of protons makes 86. You know, 86 minus 2 makes 84. So that makes this atom polonium. Pretty simple so far. You do the same thing with other things that you lose, like beta particles and whatnot. Alright, so the book gives also another practice thing we can do. This is a partial reaction. So they show you uranium decaying to thorium. So, and they give you the masses of both and the amount of protons that each one has, and you need to tell what the other component is that comes out of the uranium, so that it can turn to thorium. So you're just going to subtract across the top, right? So 238 plus 234, or minus 234, sorry, it makes 4, pretty simple. 92 minus 90 makes 2. What did we see earlier that has 4 and 2 for its symbols? It's the helium or the alpha particle. So you would say that uranium decayed and lost an alpha particle. So there you go. Alright, so the book talks about predicting radioactivity in elements. I really never found this important, or I really had to learn it at all, but there's a couple brief rules, so I guess I'll explain it. First one is, this is the easiest one, is that Z being the like the number of protons. If you remember back when we did a effective nuclear charge last chapter, that was ZF or Zeph. So I shortened it to be, but so if there's more than 83 protons in an element, so if it's past bismuth on the table, it's going to be radioactive and will decay. The other thing the book talks about is the ratio of neutrons to protons. So from numbers 1 to 20 on the table, stable isotopes will have a neutron to proton ratio that's very close to 1, but from 21 to 83, the ratio for stable isotopes changes from the ratio from neutrons to protons changes from like 1 to 1.5. So a stable isotope of let's say tin might have 50 protons and maybe 75 neutrons. Just off the top of my head, something might happen. Just because 1.5 would be the ratio, or close to it. So, not super important. I wouldn't spend a lot of time learning it, but it's the one I have written down there is pretty basic. Alright, well, now we're getting into radioactive decay. This is something that might be kind of tricky for you guys, because the way the book is set up, you're not going to have kinetics till the end, but I am following the book, so I'll do my best to teach it this way. So, first equation they give you is the rate in disintegrations per second is equal to a unknown constant that's unique for like every element at different it's different for every element at different temperatures, so it's kind of a weird thing. It's actually a lowercase k. You probably can't tell from how I wrote it, but it's supposed to be lowercase k, and then n. So k is a constant. I'll just stop it. Constant, and n is number of radioactive nuclei. So with some calculus, you will integrate. Your teacher will probably make sure you know how to do this, but it's not, the integration part is not that important. The result is, so with some integration, you get to have ln n0 over n at a certain time equals this little constant k again times the time. So where n sub 0 is it's going to be the original number of radioactive atoms, and nt is the amount of radioactive atoms at time t after t seconds. So, and k is the rate constant, which you will learn about a lot more when you do kinetics, but it's in the unit of s to the negative 1 over seconds, and t is time in seconds. So, yep. Finally, the important thing to do is find out a equation for half-life. So, with some more math that isn't super important, what's important is the result. So, the resulting equation, you'll get t half, which stands for half-life, so the time it takes for the half-life to occur, is going to be equal to 0.693, or to be more specific, that's lowercase k again, by the way, sorry, but so this is the ln of 2. This happened from simplifying the last equation with using values that would make the equation be a half-life equation. Alright, so this is you should have a good idea of what half-life means, but if you don't, it's the time it takes for half of a certain substance to decay and have only half of itself remaining. So, another weird thing with half-lives, well, it's not weird, it makes perfect sense, but some people don't really think about it at first, is that if the first half-life goes by, you go from the full amount you had to half that amount. Well, the second time that same amount of time goes by, the next half-life, you don't go from half to 0, you go from half to a quarter, and so on and so forth. So, the fraction left, if you just want to solve it really fast, is 1/2 to the power of h, where h is the number of half-lives. I've also seen it done where people use the half-life, but or this equation to find out how much is left, but instead of plugging in the amount of half-life, they plug in the amount of time divided by the amount of time that the half-life is. So even if you don't have a perfect amount of half-lives, like a round amount like 3, which would get you to 1/8, you might have you might just have, it was going for 40 seconds, and you knew the half-life was 25 seconds. You could do 1/2 to the power of 40 over 25. So, that would also work if you were just trying to find a quick way, but this only works for half-lives. It won't work later in kinetics, so don't make that too much of a habit. So this is just a simple example problem. If I told you I had 100 grams of a certain substance, and then told you the half-life of this substance was 20 days, and that 40 days had passed, and I asked you how much of the original substance remained, you would do it probably pretty easily. So 20-day half-life, obviously that goes twice into 40, so that means it's gone through half-lives twice, so you can just, if you want to even just use the equation, I mean, it's pretty easy to figure out, but 1/2 has gone through 2 half-lives. 1/2 to the power 2 equals 1/4. So 1/4 of the original amount remains. 1/4 times 100 equals 25 grams. Yay! Easy equations. Alright, so similarly we'll practice with the other equation. So if they told you half-life is 20 days, like in the last problem, they also might ask you to solve for K, the rate constant. So what you're going to do is you're going to set it up, right? We know that the half-life is equal to 0.693 over 20. So, and we know the half-life is not over 20, I'm sorry, over K. I'm thinking over 20 because that's what our number is. So we get 20 equals 0.693 over K. And it's really just simple algebra. 20K equals 6.93. Is it K? It's awful. Alright, equals 0.693, and then you divide each side by 20, and you get K equals, 1 sec while I calculate, equals 0.0346, and I'll just stop there. Alright, not too bad, right? Alright, well, the last thing this thing really goes into, and I'm not going to spend too much time on it because it's probably won't be at all important on your test, is that nuclear fission and nuclear fusion. Well, the things you should know about nuclear fission is that it produces, I'll start making a little list here. Fission produces, it's like radiation, so I'm going to just say pollution. So you can just be like radioactive. I'll just do that little picture thing going. Also, energy, pretty good energy, but that's not pollution, that's just another thing. Whoops. Alright, well, and then it's used weapons, so just a few things fission's good for, and it's really just, they shoot like a standard reaction. They shoot like a uranium-235 with a neutron, and it splits into it splits with a lot of released energy into like bromine 87 and lanthanum 146, and also shoots out 3 neutrons, and those 3 neutrons will hit 3 other uranium atoms, uranium-235s, and make another reaction. So that's how fission works. It just splits and splits and splits until you're all out of fissionable or fissile material. Fusion, on the other hand, is a lot more preferable, but it takes a lot more energy to start. Fusion makes no pollution, so that's how you start seeing it as a possible fuel source in the future, like you hear about plasma ion fusion torches. And then there's no pollution, lots of energy, it's a big E, and it's what the sun does. The sun combines hydrogen atoms to make helium, so lots of energy there, but it also takes a lot of energy to cause it to happen. High temperatures, a lot of forces, so that's why we don't have fusion now. But all in all, not awful.